Welcome everybody to today's deep learning lecture. Today we want to talk a bit about common practices, the stuff that you need to know to get everything implemented in practice.
And there is very little theory behind the best solutions.
So I have a small outline over the next couple of videos and the topics we will look at. So we will think about the problems that we currently have and how far we went. Then we talk about training strategies, again optimization and learning rate and a couple of tricks how to adjust them, architecture selection and hyperparameter optimization. One trick that is really useful is ensembling, and typically people have to deal with class imbalance, and of course there's also very interesting approaches how to deal them. So finally we look into the evaluation and how to get a good predictor how well our network is actually performing. Okay, so far we have seen all the nuts and bolts of how to train the network. We have the fully connecting convolutional layers, we have the activation function, the loss function, optimization, regularization. And today we will talk about how to choose the architecture, train and evaluate a deep neural network. And the very first thing is test data. Test data goes into the vault. Ideally, the test set should be kept in a vault and be brought only out at the end of the data analysis, as Hasty and colleagues are teaching in the elements of statistical learning. So first things first, overfitting is extremely easy with neural networks. Again, ImageNet random labels. So true test set error and generalization can be underestimated substantially when you use the test set for model selection. Not a good idea.
Because it doesn't work.
So when we choose the architecture, that's typically the first element in the model selection. And this should never be done on the test set. So we can do initial experimentation on a smaller subset of the data, try to figure out what works, but never work on the test set when you're doing these things of selecting the architecture.
There's no notion of evil in that context, other than the fact that people die.
Okay, so let's look at a couple of training strategies. Before the training, check your gradients. Check the loss function, check own layer implementations, that they compute correctly. And if you implemented your own layer, then compare the analytic and the numerical gradient. You can use the centered differences for the numeric gradient. Then you can use relative errors instead of absolute differences and consider the numerics. Use double precision for checking. Temporally scale the loss function if you observe very small values, and choose your age for the step size appropriately. Then we have a couple of additional recommendations. If you only use a few data points, then you will have less issues with non-differentiable parts of the loss function. You can train the network for a short period of time and only then perform the gradient checks. You can check the gradient first, then with regularization terms. So if you first turn the regularization terms off, check the gradient, and then with the regularization terms, and you turn off data augmentation and dropout. So you typically make these checks on rather small data sets. So the goal of the initialization is that you have a correct random initialization of the layers, so you can compute the loss for each class on the untrained network with regularization turned off. And of course, that should give a random classification with an untrained network. So you then can compare the loss with the loss achieved when deciding for a class randomly, and they should be the same because you randomly initialize, and then you repeat with multiple random initializations just to check that there's nothing wrong with the initialization.
And nothing in machine learning is exact.
Let's go to the training. First, you check whether the architecture is in general capable of learning the task. So before training the network on the full data set, you take a small subset of the data, maybe 5 to 20 samples, and then try to overfit the network to get a zero loss. With such few samples, you should be able to memorize the entire data set and try to get a zero loss. So then you know that your training procedure actually works and you can really go down to the zero loss. And optionally, you can turn off the regularization because it may hinder this overfitting procedure. Now, if the network can't overfit, you may have a bug in the implementation. Your model may be too small, so you may want to increase the parameters or the model capacity. Or simply the model may not be suitable for this task. Also, get a first idea about how the data, the loss, and the network behave. Remember, we should monitor the loss function. These are typical loss curves. Make sure you don't have an exploding or vanishing gradient, but you want to have the appropriate learning rate. So check the learning rate and then identify large jumps in the learning curve. If you have very noisy curves, try to increase the batch size. So noisy loss curves can be associated with too small mini batches. Next thing, get a validation dataset and monitor the validation loss. You remember this image here. Over the epochs, your training loss will of course go down, but the test loss would go up. And you never compute, of course, this on the test dataset, but you take the validation set as a surrogate for the test loss, and then you can identify whether overfitting occurs in your network. If training and validation loss diverge, you have overfitting, so you may want to increase the regularization or try early stopping. If training and validation loss are close but very high, you may have underfitting, so decrease the regularization and increase the model size. You may want to save intermediate models because you can use them for testing later. Further, during training, monitor the weights and the activations. So keep track of the relative magnitude of the weight update. They should be in a sensible range, maybe 10 to the power of -3. With the convolutional layers, you can check the filters of the first few layers. They should develop towards a smooth and regular filter, and you may want to check that you get filters like here on the right hand side. The ones on the left hand side contain considerable amounts of noise, and this may be not very reliable features. So you may start building a noise detector here. So this can be a problem. Also check for large or saturated activations. Keep in mind dying reloads may happen.
Machine learning is the science of sloppiness.
Okay, so let's look a bit at optimization and the learning rate. You want to choose an optimizer. Now, batch gradient descent requires large memory, is too slow, too few updates. So what people go for is typically stochastic gradient descent, but here the loss function and the gradient become very noisy, and in particular if you only use one or few samples. So you want to go with the mini batch. The mini batch is the best of both worlds. It has frequent but stable updates. The gradient is noisy enough to escape local minima, so you want to adapt the mini-sized batch to yield more smoother or more noisy gradient depending on when your problem in the optimization is. In addition, you may want to use momentum to prevent oscillations and speed up the optimization. So the effect of hyperparameters is relatively straightforward. The recommendation from us is you start with mini-batch, stochastic gradient descent and momentum, and once you have good parameters set up, you then change, for example, to Adam or other optimizers that can optimize the different weights with an adapted learning rate. Keep in mind, observe the loss curve. If your learning rate is not set correctly, you have trouble in the training of the network. And for almost all gradient-based optimizers, you have to set EDA. So we often see that directly in the loss curve, but this is a simplified view. So we actually want to have an adaptive learning rate and then progressively have smaller steps to find the optimum. So as we already discussed, you want to anneal the learning rate. Now, annealing the learning rate or learning rate decay is yet another hyperparameter that you have to set somehow. You want to avoid oscillations as well as too fast cooldown. So there's a couple of decay strategies. Stepwise decay, every n epochs, you reduce the learning rate by a certain factor, like 0.5 or a constant value, like 0.01, or you reduce the learning rate when the validation error is no longer reducing. There's exponential decay at every epoch, You actually use this exponential function here that can control the decay. There's also the 1/t decay that at epoch t you essentially scale the initial learning rate with 1/1 plus kt. So the stepwise decay is most common, and also the hyperparameters are easy to interpret. Second order methods are currently uncommon in practice as they don't scale very well. So much about learning rates and a couple of those hyperparameters.
The stuff that works best is really simple.
Next time in deep learning, we will look further into how to adjust all those hyperparameters that we've just discovered, and you will find those hints to be really valuable for your own experimentation. So thank you very much for listening, and see you in the next lecture. Bye-bye.